Alright. So tonight we're going to continue multiple regression. I'm Ramya, I'm the IT coach. And tonight we're going to be doing interpretation of the multiple regression parameters. And then we'll perform some tests for the multiple regression parameters. Alright. For the sample multiple regression function, my function is y equals b0 plus b1 x1 plus b2 x2 up to bn xn. So what we're going to look at now is what do B0, B1, B2, B3, what do they represent and do they have any practical meaning? So B0 represents the y-intercept of a sample multiple regression function, which is the fitted value of y when x1 equals x2 up to xn equals 0. So when you don't have any values for x, all the x's, the y-intercept is the B0. Y-intercept is the value on the y-axis where the line, the regression line, meets the y-axis. That's your y-intercept. So that's B0. B1 to Bn, they each represent the slope with respect to a particular predictor variable of a sample multiple regression function. So B1 through Bn are the slope values. The y-intercept B0 has a practical meaning for data sets in which x1 equals x2 to xn equals 0 are meaningful values, and the sample data exists at or near x1 equals x2 up to xn equals 0. So it depends upon what survey we are doing, what kind of experiment we are doing, what kind of study we are doing. If for x1 equals x2 up to xn equals 0, if there are no x values, if I can have a y value still, then B0 would have some practical meaning. But sometimes when the value of x is 0, B0 will have no meaning. For example, last week there were a few examples in Zybooks, and even this week they continue the same examples. One of them is finding the percent body fat using the mid-arm circumference, the thigh circumference. So if you recollect this example, x1, x2, x3, those are your predictor variables. And those are your thigh circumference, the mid-arm circumference. Imagine having x1, x2, x3 as 0, which means there is no value for the thigh circumference or the mid-arm circumference. So when x values are 0, when you don't have any value for the circumference, there is no question of having a y, which is a percent body fat. So first of all, it's not possible for someone to have 0 values for the circumference, mid-arm. So having a y value when x is 0 makes no meaning. So B0 in this example will have no practical significance. But there will be some examples where B0 would still have some practical meaning. Then B1 through Bn, they always have a practical meaning because B1 through Bn, those are your slope values. They represent the change in the y for unit change in x. So if I'm considering a small change in my x values and I have a corresponding change in my y values, if I divide the change in y over the change in x, that gives me the slope, which is B1 through Bn. For example, if my mid-arm circumference changes by 1 unit, the percent body fat in a person might change by a certain amount. So B1 then would have some meaning because it's giving me the change in the percent body fat in a person when the mid-arm circumference increases. So B1 through Bn will always have some meaning. But B0 may or may not have any practical significance depending upon the study that you're doing. Any questions? B0 is the y-intercept. If I try to draw it, I'm not sure if, are you looking for what B0 is in the graph? So if I have my graph like this, and let's say my regression line is something like this. This distance from zero up to this point on my y-axis, this distance is B0. So this entire distance is B0. Because here, all my x values are 0 at this point. At the origin, all my x values are 0. So I still have a value for y. So depending upon what study you're doing, what experiment we are doing, this may or may not have a practical significance. But when you draw your regression line, you will have this B0. There will be a value for B0. Because if you extend the line, it will always cut the y-axis at some point. So you will always have a value, but whether or not it has any practical significance, that depends upon the study that you're doing. Yeah, for certain examples, B0 will not mean anything to you. For example, for the percent body fat, as I said, you cannot have 0 values for mid-arm circumference or the thigh circumference. That's not practically possible. So in that case, there is no point having a B0 value. Because when x is 0, there should not be any value for y. There should not be any percent body fat. Yes, in the example that I am saying, B0 is useless. But there might be some studies where B0 would still have some practical significance. I'm trying to think. There was one example in Zai books where they talk about, I think, the level of the disease, and the predictor variables were maybe the treatment that was given. So when no treatment is given, which means the predictor value is x is equal to 0, when no treatment is given, the disease is there. In that case, your B0, which is showing your disease level, is still there. And that makes sense because if you're not giving any treatment, the disease is there. So in that example, B0 does have some meaning. Okay, the residual mean square error. So the residual mean square error is given as the square root of the residual mean square, which is nothing but the square root of the residual sum of squares over n minus p. So in the last couple of weeks, when you're reading Zai books, you might have come across all these definitions, what each of these mean. So n is the sample size, p is the number of regression parameters. The residual standard error is a measure of the precision of a model's prediction. A relatively small residual standard error indicates that the actual future value of y is likely to be relatively close to the predicted value. Less residual standard error is preferred. So when we run a set of Python code. I think last week also we had the code. When you ran it, we did get the residual sum of squares. So if we get the values from the Python code divided by n minus p, that will give you the residual mean square value, and then take the square root of that. That should give us the residual mean square error. And we always want to have a small value for the residual mean square. The smaller the value, the better is your regression line in describing your set of points. And it will give you an almost accurate value for future predictions. Here is an example. Consider the body fat data set and a model where the response variable y is % body fat and the two predictor variables are x1 triceps skin fold thickness and x2 mid-arm circumference. Let's find the residual mean standard error. So here we have the Python code. We're using the OLS function. And then you're printing out the ANOVA table. So in the results, the first value, 389.455, that is your explained variation, which is your regression sum of squares. But we don't need that right now for this calculation. I just wanted to let you know that's the explained variation. The unexplained variation is your residual sum of squares, and that's the lower value. So we want to take this lower value, then you want to divide it by n minus p. N is the sample size. It was given in the question that n was 20. And p is your number of regression parameters plus 1. So we have two parameters here, x1 and x2. So p is parameters plus 1. So we say 20 minus 3. So when you evaluate that, you get 6.231. 20 was given, yes, it was given in a different place in Zybergs because this example they keep giving again and again, the body fat one. And at one place, I remember saying that 20 was the sample size. So it wasn't actually given in here, but it was given in a different part, I think in the same section. So 20 is the sample size. P is the number of parameters plus 1. So here, see, P is n plus 1, the number of regression parameters. So in our example here, we have x1 and x2 as the parameters. So plus 1 would be 3. And then you just take the square root of that, it's 2.496. That's your residual mean square, mean standard error. Next part is testing the multiple regression parameters. So let's consider the model y equals beta 0 plus beta 1 x1 plus beta 2 x2 up to beta n xn plus epsilon, which is the regression error. If a parameter is 0, then the corresponding predictor is redundant. There are two tests to determine if a predictor variable needs to be removed. So here what we're trying to do is, sometimes we might have an experiment where my predictor variables, which are x1, x2, x3, where there might be one of them or more than one of them which are redundant, which are not really helping or contributing towards the y value. So in that case, what would happen is, if they don't have a relationship with y, then your slope values, which are your beta 1, beta 2, those values would be 0. If there is no change in y for any change in x, then the slope is going to be 0. Then in that case, beta 1 or beta 2 or beta 3 will become 0. So there's no point having that term at all in the regression equation. So we want to remove that term. So we want to now find out, is there a term which needs to be removed? And there are two ways of doing this. There are two tests that we can do. One is the overall F test, and the other one is the individuality test. The overall F test is to determine whether a linear relationship exists with at least one predictor variable. So here my null hypothesis would be that there is no relationship. So all my regression parameters are equal to 0. So beta 1 equals beta 2 up to beta n, they're all equal to 0. That's my null hypothesis. The alternate is at least one, there is at least one beta value which is not 0. So it could either be beta 1 or beta 2 or beta 3. We don't know which one. This test will only tell us whether there is at least one beta value which is not 0. The individual t-test, on the other hand, it is used to determine whether a single variable has an effect. Here, you can pick one parameter and we can test if that parameter is 0 or not. So the null hypothesis is saying that bi equals 0 for some I equals 1 through n. So here it can be beta 1 or beta 2 or beta 3. I can test and say, I want to test whether beta 1 is equal to 0. So my null hypothesis would be beta 1 equals 0. Alternate would be beta 1 not equals 0. So here I'm being more specific about which parameter I want to test. In the overall F test, you will not be able to test a single parameter. You can just test whether there is at least one parameter which is not 0, but you will not know which one. But the individual t-test is more precise. It helps you find out if there is or which one exactly is not equal to 0. So let's look at both the tests. First, we'll do the overall F test. So we set the null hypothesis. Null hypothesis is beta 1 equals beta 2 up to beta n equals 0. And the alternate is that there is at least one beta I not equal to 0 for I equals 1 through n. Then you find the F statistic. So when you're using Python and we get the output, these values will be there in the output. So we just have to pick the values from there. So the F statistic will be there. Then the p-value will also be given in the output. So the p-value is a probability of observing an F statistic at least as far from 0 as the one observed if the null hypothesis were true. And then based on the p-value, we compare it to alpha and then we make a decision. So if the p-value is less than alpha, then we reject the null hypothesis. We conclude that there is at least one beta k which is significantly different from 0, which means that a significant linear relationship exists between y and the set x1 through xn. But if p1 is greater than or equal to the significance level, we fail to reject the null hypothesis. We conclude that no beta k is significantly different from 0, which means that a significant linear relationship does not exist between y and the set x1 through xn. So let's go ahead and look at an example. If you have any questions, you can ask me. I think this will make more sense when you look at the example. So we consider the body fat model with response variable y equals percent body fat and three predictor variables. X1 equals triceps trifold thickness. I think it's skin fold thickness. X2 is mid-arm circumference and X3 is thigh circumference. Does a linear relationship exist with at least one variable? So we have the output here. And the values that we are concerned with are the F statistic and the P value. So the F statistic is given here, 21.52. And the P value is also given, 7.34 times 10 raised to a negative 6. So it's a very, very, very small value. So our null hypothesis would be B1, beta 1 equals beta 2 to beta n equals 0. And the alternate would be there is at least one beta I not equal to 0 for I equals 1 to 3. We don't know which one it is. It could either be beta 1 or beta 2 or beta 3, but what we are looking for is that at least one of them is not 0. The slope coefficient, it would be these values. Those are your betas 1, beta 2, and beta 3 values. Yes. So the F statistic is 21.52. So F statistic is given here. It's 21.52. And then the p-value is 7.34 times 10 raised to a negative 6. And that's the value right below the F statistic. So the probability value you can see is very, very small. So the probability of getting a value as extreme as the one that we've got in our results is very, very small. So now when you compare this with alpha, p is very, very small. So we have to reject the null hypothesis. So since p-value is close to 0, sufficient evidence exists to reject the null hypothesis, which suggests that at least one of x1, x2, and x3 is linearly related to y. So here we are saying that we're going to reject the null. So there is evidence that there is at least one value which is not 0. So either beta 1 or beta 2 or beta 3 is not 0. So there is a linear relationship between y and the x values. Any questions on the overall F test? Right. Next is the individuality test. So here we will specifically test one parameter, beta 1, beta 2, or beta 3. So an individuality test considers one of the regression parameters. So my null hypothesis will be beta I equals 0. So I can be any value. So depending upon what the question is, you'll either say beta 1 or beta 2 or beta 3. The alternate would be beta I not equals 0. Again, find the t statistic, which is bi divided by the standard error of bi. This again we will get in the output. And then the p-value, this will also be there in the Python output. And then you make your decision. So we compare p with alpha. If p is less than alpha, we reject the null. If p is greater than alpha, we will not reject the null. So if the p-value is less than the significance level, we reject the null hypothesis. We conclude that a significant linear relationship exists between y and xi when the remaining predictor variables in the model are fixed. Thus, xi should not be dropped from the model. And if the p-value is greater than or equal to the significance level, we fail to reject the null. We conclude that a significant linear relationship does not exist between y and xi when the remaining predictor variables in the model are fixed. Xi should be dropped from the model, but the remaining predictor variables are retained. So let's look at an example. So it's the same example again. We consider the body fat model with response variable y equals % body fat and two predictor variables x1 and x2 at the alpha equals 0.01 significance level. Thus, the mid-arm circumference have a statistically significant effect on % body fat according to the output below. So here we are specifically testing for the mid-arm circumference. So the predictor variable here is x2. So we are checking if x2 is having an effect on the value of y. If it has an effect on the value of y, then the beta value, the corresponding beta value, which is beta 2, it will not be equal to 0 because there is a value there. Only if beta 2 is not equal to 0, we can say that x2 has a linear relationship with y. So now the null hypothesis here will be beta 2 equals 0, and the alternate hypothesis is beta 2 not equals 0. So we're going to test if beta 2 is equal to 0 or not. So the t statistic that is given in the output. So what we are testing is the mid-arm circumference, which is the third value, the mid-arm circumference. And so the last row is what we want to look at. The t value is negative 2.443, and the corresponding p value is the one in the next column, 0.026. So it is this value that you want to compare with alpha. So 0.026 is greater than the significance level. So insufficient evidence exists to reject the null, which suggests that the % body fat and mid-arm circumference are not linearly related. So that's what the null is saying, that beta 2 0, there is no relationship. But we cannot reject the null because our p-value is greater than alpha. So we retain the null hypothesis, which is beta 2 equals 0. So if beta 2 is equal to 0, which this means that x and y are not linearly related. x2 and y are not linearly related. So x2 has no effect on the value of y. So in that case, you have to drop your x2 term from your equation. Great. Is there anybody who wants me to go over this again? Any other questions? So this is pretty much what was there in this week's reading material. So the first part, you're interpreting what beta 1, beta 2 mean. And then in the next section, you're testing the parameters. And the two tests that we are doing here is the overall F test and the individuality test. Yes, we are saying that it is not significant enough. It might have some contribution, but it's very, very less. And because we are comparing it with the cutoff value, we are saying it's so less that it almost has no effect on the body fat. Any other questions? Yes, I covered all the important things for this week. So this is all I had for tonight. And I know we still have a lot of time. So if you have any other questions, I'd be happy to answer them. Which output are you talking about? The previous one? Are you talking about this chart here? Okay. So in this chart here, we've seen this output over the last two modules, this type of a chart. And the last module, we were concerned with the R squared, the adjusted R squared. And in this week, we've looked at the F statistic and the probability. The other values that we usually look at are these values, the intercept and the values below that. So the intercept is the first one, and this is the coefficient. So this is your beta 0 or the B0. This is a sample, so it's going to be B0. These are B1, B2 values. So if you're trying to build your equation based on these values, it would be y equals 6.79 plus 1.0006 x1 plus negative 0.43 x2. So that would be your equation. And then the third column here, the t values, these you would need for the individuality test. And then the next column, which is the p, again, you would need this for the individuality test. Yes, these are your slope values, 1.006 and negative 0.43. Those are your B1 and B2 values. No, we don't interpret it that way. 6.7 is the B0 value, which is your y-intercept. It is the value of y when all your predictor variables have a value of 0. So in your equation, so our equation, the way we write it is y equals B0 plus B1 x1. I'm sorry, I'm not able to write well my mouse, plus B2 x2 and so on, right? So if your x values were all 0, the B0 value is your intercept, and that is your 6.796. So if I have to draw my line, and let's say my line was something like this with all my points here, then this point on my y-axis, that's my B0 value. That's not the slope. It's called the y-intercept. It is not the slope. Slope values are B1 and B2 values. That is your change in y per unit change in x. For example, let me take 2 points in my graph. And if I try to do, if I find the slope So I mark these two places. I find the corresponding y values in my graph. And then I take the same 2 points and find the corresponding x values in the x-axis. And then I divide the change in y over the change in x. That is my slope. And that's my value which I would get for B1, B2, B3. X1, X2 are your predictor variable values. So your mid-arm circumference or the thigh circumference, those are your X1, X2 values. And those are the values here on your x-axis. So if I'm plotting, when keeping other variables fixed, if I'm plotting y over, let's say, x1, and then I find the slope value would be b1. Yes, from your study, you would have a set of x1 values, a set of x2 values. You plot them against y. What else? What other questions do you have? All right, anybody else? You're welcome. If you don't have any questions, then I guess I'll just say good night, and I hope to see all of you next week. Coefficient of determination. Sure. So we had this last week, I think. Coefficient of determination. The coefficient of determination will tell you how useful is my x value in predicting my y value. So let's take an example. Let me think. Let me open up Zybooks. I think it might be easier if I do that. Just give me 1 second so I can open up Zybooks. Then I will share my screen. So here last week we did the coefficient of multiple determination. So here again what we were doing was trying to see the value of r squared, and the r squared is telling you how useful are my predictor variables in giving me the value of y. So here for the first one, when we took just the x1 values, just the tricep skin fold thickness values, we got an r square of 0.711 here. And then we said that 71% of the body fat is explained by the triceps skin fold thickness. So my X1 values are contributing towards 71% in explaining my Y values. So the greater your R squared value, the better is your predictor value in predicting the value of Y. Yeah, you can also say that it is helping you tell you what kind of correlation it is. Yes, if it is a strong correlation, then definitely your R squared value will be more. So then you can say that X1 is strongly correlated to Y. No problem. I will see you guys next week. And I look forward to that because that's going to be like week 8. And that's probably the last time I will see you for this term.